evolution. Pattern prediction can lead to intelligence. Everything a machine sees or hears, every action it takes, even ideas themselves, they're all understood the same way, as patterns. And once a machine learns to predict patterns, it can also create them, mimicking and often exceeding human ability.
So I think the situation we're in now is like someone who has a very cute tiger cub. A tiger cub makes a great pet, but you better be sure that when it's grown up, it never wants to kill you.
This is what we now call AI, a giant pattern prediction machine that succeeded by copying nature's solution to learning. You could say nature solved learning 3 times in 3 different layers. The first layer is evolutionary learning, which is built on a simple strategy: try random things and see what survives. But this is a very slow learning process that happens across generations and cannot adapt to rapid environmental changes in life. So nature discovered a second layer of learning, which was much faster, using a brain to adapt behavior within a lifetime. Brains allow organisms to explore randomly and then do more of what works based on the experience of rewards or pain, known as reinforcement learning. This is the basis of the AI paradigm of machine learning. Instead of trying to program a machine with instructions, we let it learn everything from scratch with a learning signal. Truly mimic a brain, machines needed one. Machines needed their own sense, that is, the ability to recognize patterns on their own, what we call abstraction. Forming abstractions is something you do automatically, ignoring trivial differences while focusing on the underlying similarities. This is what the great writer Borges brought to life in his short story about a man who couldn't form abstractions. Instead, he had a perfect memory, remembering every leaf of every tree, every cloud formation, every ripple in water from days past. But this power came with a downside. Because he noticed every difference, everything was different to him. His own face surprised him every time in the mirror. It bothered him that the word dog embraced so many different-looking creatures. And it was strange to him that even the same dog seen from the side would have the same name as the dog seen from the front. Abstraction allows you to ignore differences that don't matter and pay attention to the shared patterns behind things. And to build a machine that could learn abstractions, researchers looked to nature for inspiration. In the late 1800s, scientists studying brain tissue had discovered the brain wasn't a solid mass, but a vast network of neurons firing in layers. And these neurons fired in chains, forming circuits that created cascading patterns of activity, processing information as it moved deeper through the layers in the brain. And so when you see a cat or a dog, if we look at the first layers of neurons in your brain, it would be hard to tell these 2 patterns apart at first. But as these signals pass through deeper layers of your brain, they begin to separate into distinct patterns of activation. By the deepest layers, a cat and a dog trigger very different groups of neurons. And in fact, all of your thoughts exist as unique patterns of activation deep in your mind.
And that's not meant to be a joke. That's what I believe a thought is. A thought is an activity pattern in a big bunch of neurons.
In fact, scientists can now look at your brain activity and tell you what image you're thinking of. This is what Frank Rosenblatt set out to build in 1958. Artificial brain tissue made of electrical components. He used transistors, tiny electrical switches, as artificial neurons, wiring them together in 3 layers. The first layer connected to an artificial retina that read pixels from an image, while the deeper layers just used random connections designed to evolve through learning. The output was simple: 2 light bulbs, one representing a square, the other a circle. And his network learned through trial and error. Each connection between neurons was controlled by a dimmer knob, adjusting the flow of electricity, a mechanical version of how brains strengthen or weaken connections. And so at first, when shown an image, the network would be uncertain about what it is, activating both the circle and square output. To train it, Rosenblatt wiggled the knobs of every connection and observed the output and kept the changes that helped. After enough examples, it no longer needed adjustments and recognized patterns on its own.
That's the basic algorithm. You're going to tinker with weights and just keep the tinkers that change.
And this is the basis for how all AI learning works today. And the breakthrough came when AI achieved nature's third layer of learning, language. Evolution selected for language because it allows learning from other people's experiences using your imagination. And realize that with language comes a general purpose imagination, anything you can put into words. While game AI could only imagine moves in chess, language could let AI imagine anything. And so to achieve this breakthrough required pursuing a broad goal, understanding language itself. The key to this puzzle came from the ultimate puzzle solver, Claude Shannon, father of information theory. In the 1940s, he helped us see language itself as a sequence of predictions, where each word you say is chosen from a set of likely words given what came before. Building on this foundation, in the 1980s, researchers began training tiny neural networks to predict the next word in text. Just like how networks learn to predict possible next moves in games, these networks learn to predict possible next letters. And the first researchers discovered something remarkable. These networks learned to cluster similar words together, verbs with verbs, nouns with nouns, and even words with similar meanings. And all of this emerged automatically from predicting next letters.
The hard part was to realize that training these neural nets to predict the next token is a worthwhile goal at all. And it influenced our thinking a lot.
An important point was 2015 when Andrej Karpathy demonstrated that when trained on enough text, these networks could not only predict patterns, but generate them. After training, he would feed it a starting phrase and loop the output back to the input, and it would continue the pattern it had learned, creating convincing writing in different styles, from Shakespeare to math. It was a shocking result. So the year after, Alex Radford at OpenAI took this experiment further, training a larger network on millions of Amazon reviews. Looking inside this network as it processed text, they found a familiar pattern. Just like vision networks built up from simple edges to complex shapes, these networks built up from simple grammar to complex ideas.
From climate change to curing diseases to disposal of plastic waste, what if they all had the same solution? A solution so tiny it would be invisible. I'm inclined to believe this is possible thanks to a recent breakthrough that solved one of the biggest problems of the last century: how to determine the structure of a protein.
It's been described to me as equivalent to Fermat's last theorem.